The basic idea behind a PID controller is to read a sensor that compute the desired actuator output by calculating the proportional, integral, and derivative response, and summing those three components to compute the output. The proportional component depends only on the difference between the set point and the process variable. This difference is referred to as the error term. The proportional gain determines the ratio of the output response to the error signal. For instance, if the error term has a magnitude of 10 and a proportional gain of 5, would produce a proportional response of 50. In general, increasing the proportional gain will increase the speed of the control system response. However, if the proportional gain is too large, the process variable will begin to oscillate. The integral component sums the error terms over time. The result is that even a small error term will cause the integral component to increase slowly. The integral response will continually increase over time unless the error is zero, so the effect to drive the steady-state error to zero. Steady-state error is the final difference between the process variable and the set point. The derivative component causes the output to decrease if the process variable is increasing rapidly. The derivative response is proportional to the change of the process variable. Increasing the derivative time parameter will cause the control system to react more strongly to changes in error term and will increase the speed of the overall control system response. Most practical control systems will use a very small derivative time because the derivative response is highly sensitive to noise in the process variable signal. If the sensor feedback signal is noisy or if the control loop rate is too slow, the derivative response can make the control system unstable. The PID controller algorithm is a robust and simple algorithm that is widely used in the industry. The algorithm has sufficient flexibility to yield excellent results in a wide variety of applications and has been one of the main reasons for the continued use over the years.
Here we have an example of a PID application for controlling a set of robotic joints. The aim of the controller is to manage the actuation of the various joints within the robot in order to attain a specific position in a manner that is accurate, timely, and efficient. If you imagine a typical closed-loop control system, for our situation, our sensor value is the output potentiometer voltage, which represents the actual joint position. Simultaneously, a desired joint position is sent to the system. From these two values, we can then compute the error between them and then apply our PID algorithm to it. The output of the control loop is then a voltage proportional to the desired motor speed, which is used to actuate the motor joints to a desired position. In order to physically implement the controller for the robot, as is often done, we decided to implement the controller digitally using a microcontroller, or in our case, an Arduino. As we can see from the video, a set of desired joint positions is set to the robotic arm, from which the error relative to the actual position, read from the potentiometer as mentioned, is computed and to which the PID loop is applied. The result of this is that the robotic arm reaches its commanded positions accurately and without any significant delay.